And to go from one to the other, well, x plus 2y plus 4z needs to go through the value 7. If you're moving along any path from q0 to q1, this thing will change continuously from 11 to 3. At some time, it has to go through 7. Does that make sense? So to go from q0 to q1, we need to cross p at some place. So they're on opposite sides. Okay. Now, that doesn't quite finish answering the question that we had, which was, where does the line intersect the plane? But, well, we can do the same thing. Now we know not only the points q0 and q1, we know actually any point on the line, because we have that parametric equation up there telling us where is the point that's moving on the line at time t. So what about the moving point q of t? Well, let's plug its coordinates into the plane equation. So we'll take x of t plus twice y of t plus 4z of t. Okay, that's equal to, well, minus 1 plus 2t plus twice 2 plus t plus 4 times 2 minus 3t. So if you simplify this a bit, you get 2t plus 2t minus 12t. That should be minus 8t. And the constant term is minus 1 plus 4 plus 8 is 11. Okay, and we have to compare that with 7. Okay, question is this ever equal to 7? Well, so q of t is in the plane exactly when minus 8t plus 11 equals 7. And that's the same. If you manipulate this, you will get t equals 1/2. Okay? In fact, that's not very surprising. If you look at these values, 11 and 3, you see that 7 is actually right in between. It's the average of these two numbers. So it would make sense that it's halfway in between q0 and q1 that we will get 7. Okay. And then at that time, q at time 1/2, well, let's plug the values. So minus 1 plus 2t will be 0. 2 plus t will be 2.5, or 5/2. And 2 minus 3/2 will be 1/2. Okay? So this is where the line intersects the plane. So you see that's actually a pretty easy way of finding where a line and a plane intersect each other. If we can find a parametric equation of the line and an equation of the plane, then we basically just plug one into the other and see at what time the moving point hits the plane. And then we know where it is. Okay, are there questions about this? Yes? Sorry, can you say that? Yes, so what if we don't get a solution? What happens? So indeed, our line could have been parallel to the plane, or maybe even contained in the plane. Well, if a line is parallel to the plane, then maybe what happens is that when we plug in the positions of a moving point, we actually get something that never equals 7, because maybe we get actually a constant. Say that we had gotten, I don't know, 13 all the time. Well, when is 13 equal to 7? The answer is never. Okay, so that's what would tell you that the line is actually parallel to the plane. You would not find a solution to the equation that you get at the end. Yes? So if there's no solution at all to the equation that you get, it means that at no time is the traveling point going to be on the plane. That means the line really does not hit the plane ever. So it has to be parallel outside of it. On the other hand, if the line is inside the plane, then that means that no matter what time you choose, you always get 7. Okay, that's what would happen if a line is in the plane, you would always get 7. So maybe I should write this down. So if a line is in the plane, then what do I want to say? When we plug x of t, y of t, z of t into the equation, we always get well, here in this case, 7 or whatever the value should be for the plane. Okay. If the line is parallel to the plane, in fact, we get, let's say, another constant. So, in fact, when you plug these things, normally you get a quantity that's of a form something times t plus a constant, because that's what you plug into the equation of a plane. And so in general, you have an equation of a form something times t plus something equals something, and that usually has a single solution. And the special case is if this coefficient of t turns out to be 0 in the end, and that's actually going to happen exactly when the line is either parallel or in the plane. In fact, if you think this through carefully, the coefficient of t that you get here, c, it's 1 times 2 plus 2 times 1 plus 4 times minus 3. It's the dot product between the normal vector of the plane and the vector along the line. So, see, this coefficient becomes 0 exactly when the line is perpendicular to the normal vector. That means it's parallel to the plane. So everything makes sense. Okay, if you're confused about what I just said, you can ignore it.